Real quick, so yesterday we covered single replacement, and we also covered decomposition. Decomposition, that takes AB, and what do you do with AB? You separate it to A and B. Now, there's two things it can split into. Go back and look at decomposition. You can get these notes out. Very good. It can split into elements and ions. Number two, yesterday we covered single replacement. How can you recognize a single replacement reaction?
Because it only changes one.
Okay. So you have one single element trying to interfere with or mix with or swap places with an element that's in a compound. You don't have any of them?
She's been here. I've been here. That's okay. Just spring break Sunday.
All right. Now, that's exactly what I want. That's exactly what I want. And when I look at this reaction right here, what type of reaction is this? It's a single. So you've got one single element, okay, please listen, one single element trying to swap places with something that's already in a compound. Okay, so that's the idea of a single replacement. What must you look at in order to tell if this thing can even work? Yeah, that activity series, okay? That chart is called the activity series. The only time you use that chart is when, Carrie, you may want to get one of these, is when you are using single replacement reactions. Okay? It's the only time you're going to use this. Now, here's the good news. Today we're going to cover double replacement. And the good news about double replacement reactions is that you don't have to look at that sheet. It works no matter what the reaction is. Okay? It works no matter what the reaction is. So, the first thing that I need you to know is that this is what it occurs between ions, please highlight this, in an aqueous solution. It occurs between ions in an aqueous solution. So basically I take this solution that looks like a liquid, okay, and I take this other solution that looks like a liquid, but are they pure liquids? No, they've got other stuff mixed in them. You just can't see it. Now, sometimes the solutions are colored, and based on the color, you can possibly tell what the solutions are, but we're not going to get into that. But you take these two solutions and you mix them together. Okay? So a reaction will occur when a pair of ions come together to produce at least one of the following. So there's three things it could potentially produce. Now, what are ions? All right, so basically what I'm trying to get you to understand is that if I have a solution of NaCl, and I could take a magnifying glass and look in that solution down to the molecular level, will you see NaCl bonded together? These are ions in solution. Will you see those two stuck together? What will you really see? Na plus Cl minus. Why will you see that instead? Those are ions. Okay. Now, there are a few cases where you may see one or two of these things together, but most of them will be like this in solution. Okay? All right, so there's three things that it can come together to form. The first thing that can possibly come together and form is a precipitate, which is also a what? Solid. Very good. All that is a solid. Now, if you'll do me a favor, if you'll look down, do you see a list of things that say 1 through 6 down at the bottom? Or it's maybe on the next page. Do y'all see that?
It's 1 through, yeah.
Okay. Are we on that? Are we that far yet?
No.
Okay. All right, but if you'll turn over and look on the back page. Those things are called solubility rules. And those rules will tell you if a solid is going to form. We're going to look at those in just a second. The second thing that could possibly form is a gas. All right. There are a few ways that you could know a gas was formed. You guys tell me, what are some ways that you could possibly recognize a gas was formed? Smell. Very good. What else? What do you mean blows up? Let's just say it if it inflates the container. How about that? Like if you're trying to do it in a balloon. Inflates container. What are some other ways? What? Potentially, but not really what I'm looking for. Anything else? What is a gas and a liquid? Bubbles. Very good. Bubbles is another way you could tell. Yesterday, Tyler, you helped me do that. How do we know that a gas was released from that demo? No, not so made a noise, but what did it do to make that noise? It didn't put it out. It actually, it ignited. Very good. Yeah. When you put the fire into that container, the noise just came from the container. Like if you have different amounts of water in glasses, it makes different noises. The reason it was such a high-pitched noise is because that container was really small. But when you put the fire into the container, the gas actually ignited and popped, okay, because of the container. Now, the pitch was just because of the little tube. Essentially. Now, you said it didn't, that one ignited, but what else could it have done? It could put out. Okay, it could put flame out. So if I have a flame lit like a candle, how do I get it out? Okay, what am I blowing on it?
Air.
Carbon dioxide. So if you have a container that has a reaction that produces carbon dioxide and you put a flame in it, what's going to happen to the flame? It's going to go out. Okay, it's going to go out. So if I take a bottle, if I were to take, what happened to that bottle? If I were to take this bottle that I just had, and I were to light a flint, okay, and I were to drop the flint down in here, would it continue to burn? Hold on. So again, if I tried to relight a flame in that, would it work? No. Last year, and I even hesitate and reservate saying this because y'all are going to want to do it, but we actually sucked an egg into a bottle last year. Okay, have you ever seen that? Okay, somebody has to bring a boiled egg that has been peeled of the shell if you want to do it. Okay, what? You can get it out.
Are you choking yourself?
No, I'm trying to fix this. Okay, all right. So again, there's a few ways you can tell a gas has been produced. Those are some of the ways. And the last thing is water or some other non-ionized substance. What does it mean by non-ionized? Okay, it's not charged anymore. So basically, it's formed a compound. You don't have that on there? Okay. Non-ionized means the pluses and the minuses have now come together to get rid of the ions. Okay? So it may not necessarily be a solid, it may not necessarily be a gas, but it may not necessarily be water either. It can be some other type of liquid or something else. So we'll get into that. So notice what happens here. So we have AX plus BY, and then what happens? Very good. Y and X move. Does it matter the order that they are written in terms of A and Y? Can you swap A and Y? No. Very good. Say that again. Very good. Notice right here. A is written first here, but where is Y written? Second. So when you rewrite them, what must come first? The cation. So essentially what I want you just to do is this is very, very simple. Just swap the anions. Now, when you write the new compounds, are they new? What do? Check the charges. Okay, for both of these, you're going to have to check your charges. To check your charges because they are new compounds. Be very careful here. It is. X and Y. Y and X. I was talking about A and Y. When you write it, can you write it Ya? No, because Y is the anion. Now, this is something that people always want to get confused on. And it's very simple. It's a simple fix. Does it matter what order you write AY or BX? Can you swap those? Yeah, that doesn't matter. Okay, but when you write it, it has to be BX and AY. But you can swap those two. You can write it BX and AY. It doesn't matter how you write that, as long as you put the compounds in the correct compound order. All right, I did make one little typo, and again, I apologize, so I do want you to write this. You see where it has number 1? Once you flip over, it's going to disappear. So please, on the back, rewrite number 1 right there. Again, that's my fault. I should have hit enter one time, and that would have fixed that problem. So just rewrite formation of a precipitate. What is a precipitate? It's a solid. Now, I know what you're thinking. How in the world am I supposed to know that it's going to be a solid? Because that's going to be your question. I can't look at something and tell if it's going to be a solid. Let me explain. It is based on your solubility rules. Now, what are your solubility rules? Here's the best news of the day. You only have to know the first 3. You are only required to know the first 3, and it's even easier than you're thinking. Okay? By the time we get done talking about them, you're going to know what those 3 are. So again, what is a precipitate? It's a solid. How do you know if it's going to be a solid? Based on solubility rules. All right, so let's look at the first 3 solubility rules that you must know. Now, I'm not even going to read the other ones, but they are there for your reading pleasure. These equations that we're potentially going to get into are called net ionics. This is a topic that will be covered to a much greater extent in AP, so we're not really going to get a whole lot deeper in this class, but once you take AP, you're going to have to know how to do it. So rule number 1, so again, these are the 3, the first 3 are the only 3 that you are going to be required to know by memorization. You don't have to know the other ones. Number 1, all common compounds of group 1 and ammonium. First of all, what is ammonium? NH4 positive are all. What does soluble mean? No. It dissolves. Soluble means dissolves. So anytime you have a compound with a group 1 or, ammonium, what is it going to do? It's going to dissolve. So will it be a solid? No, it will not be a solid. Now this next one, the only one you're going to be tested on is this first one. All nitrates. And if you want to know acetates and chlorates, that's fine. I'm telling you, the only one you're going to be asked about is nitrates. All nitrates are what? So any compound you see that has a nitrate attached, will it ever be a solid? No. It will dissolve. This is the one that's going to get you. This is the one that has the rules applied. So far is it really simple. Group 1 ammonium and nitrates are all what? All, that's it. Here's the one you got to know. Any compound with a halogen. Now what is a halogen? Group 17, but there's something very, very, very specific. Other than who? So do me a favor, and this is my fault. I genuinely need to retake this because it doesn't sound good. So what are the halogens other than fluorine that we're talking about? Okay, all right, so the chloride ion, what else? Bromine, or the bromide ion, and what else? Iodine. So those 3. Those are the 3 we're focusing on. So chloride, bromide, and iodine. So everything other than F. Now, why don't we talk about AT? It's radioactive. We never talk about it. So essentially, you could pretty much just cross off the periodic table. We never talk about it. So these 3, notice what it says. Any compound with a halogen with a metal are what? So what does that mean? Here's where the hard part comes in that you have to memorize. Except when they are with silver, mercury, and what? Lead. So any compound with chlorine, bromine, and iodine will dissolve unless they're with silver, mercury, and lead. Now, what do I mean by heavy metal? They're just really heavy. Yeah, their atomic mass is really heavy. Okay, so these three. So chlorine, bromine, and iodine will dissolve unless they're with silver, mercury, or lead. All right, so those are the only three that you're required to know. If you want to finish reading the rest of them, that's fine. But if you're an AP, you might as well go ahead and start memorizing them. If you want to go for that. All right, so my first question is, go back, Hannah, reread me the first line under double replacement reactions. What does it say?
Occurs between ions and aqueous solutions.
Stop. Occurs between what? Ions in.
Aqueous solutions.
So look at our first two reactants. Are both of them aqueous solutions? Yes. So really, do you see these as a whole entity, as a compound? No, they're really supposed to be what? Ions. So if you have enough room, you can actually rewrite this. It should look like this. Na plus Cl minus plus Ag plus NO3 minus. Again, that's if you could take a microscope and look at it under the most atomic level, that's what will be floating around. You wouldn't have salt. Okay, it's really supposed to look like this. Do you agree that those are two couples that are just going to swap places? Yes. Do what? Yeah. So can you tell that this is a double replacement reaction? It's a compound plus a compound. You just got to recognize that. How do you know, based on solubility rules, this did not form a solid? It's a nitrate and read the first solubility rule. All group 1s. What is Na? That's a group 1 and it's a what? What is the chances of this forming a solid at all? 0. It fits two of our rules. Then let's look at the next one. You've already seen it. What does that little S behind this mean? All right, so we need to know, based on our solubility rules, how we would know this is a solid. This is the only one that you have to really, really focus on. All chlorides are, read the rule, soluble unless with who? Silver, mercury, or lead. What is Ag? That's why it's a solid. That's why it's a solid. Does that make sense? Tell me now if it doesn't. Those are the only three rules you need to know. Group 1's nitrates are soluble, and then chlorines, bromines, and iodines are soluble unless or except there was silver, mercury, or lead.
But it has an S beside it.
That tells you it's a solid.
Yeah, so it shouldn't be.
But you're going to have to tell me that part.
It's not gonna say.
No, that's not going to say that. All right, so let's look at our next example. BaCl2 plus Na2SO4. Again, both of those are ions in solution that are just floating around. We're going to have a double replacement reaction, and we're going to produce NaCl. Why is this one soluble based on your solubility rules? Why is NaCl soluble? Because it's group 1. As soon as you see group 1, it's done. But this BaSO4 has an S behind it. Do you need to know the rule of sulfates? Nope. But look, it's on there. What rule does it talk about sulfates? All right, read it for me. Read the whole thing. Stop right there. Do you agree that sulfates are SO4? Okay, keep reading. Okay, so is barium one of those? That's why it's a solid. Again, do you have to know that one? Nope, sure don't. But that's the rule. So it does adhere to the rules. You just don't have to know that one. Any questions on that? Okay. All right, so let's look at the next one. Formation of a gas. Now, we don't have any rules for your ability to know a gas has been formed. So you're not going to have to tell me this one unless you see it's an oxygen or a hydrogen or a carbon dioxide. This one's kind of the funny ones. What is HCl? Okay, this is an acid. So what we're doing is we're taking this iron sulfide solid and we're mixing it with an acid. Now, what do most solids do in acids? They dissolve. Most of them do. So notice what happens. Do you agree that that is a compound plus a compound? Do you have a double replacement reaction? Okay. What swap places? Okay. So notice the only thing that happened. The Cl came over here with S or with Fe, and where did the F go or the S go? It's now with the H. Are these two brand new compounds? Where did those subscripts come from? They weren't over here. Okay. No. You have to check your charges. Okay, you got to check your charges on these. I'm telling you. It's going to mess you up if you don't check your charges. Now, is that one balanced properly? No, it is not balanced. So it probably needs to be balanced. It's a simple balance. How do you balance it? Where? 2 in front of the HCl, and that's it. That balances that. Okay, real simple. The what? Yes, ma'am. All right. Fe and Cl are going to come together as a compound. You got to know what their charges are so you can crisscross them. Cl is a -1 because why? It's a group 17. But what is iron? You know, iron's a transition metal, right? So how do you get its charge? You got to reverse crisscross, right? Now, but what's the problem when you say negative or a +1 and -1? Is sulfur -1? Why? It's in group 16. So you have to change both of those to +2 and -2. So Fe in this case is still going to be a 2+. So when you crisscross, you get FeCl2. Okay. Hydrogen's in group 1, right? So it's a +1. Sulfur's in group 16, so it's a 2 negative. So you crisscross, you get H2S. That's what check the charges mean. Okay. Okay. Right here, do you agree that the subscripts are both 1s? So when I reverse crisscross, I get a +1 and a -1. But sulfur is in group 16. Remember what you always have to check the charge of the anion? So it has to be -2. So change both of them to 2s. Okay. All right. We're going to get into this more in a little bit. We're going to talk about how we know that this is an acid and how this is a base. So we have a formation of water. Could you recognize HCl as an acid? Who said no? Because it has an H and it's aqueous. That's an acid. What is NaOH? Anytime you have a metal plus a hydroxide. Anytime you have a metal plus a hydroxide in AQ, it's a base. So what is this NaOH? Is that a metal and a hydroxide and aqueous? It's a base. Very good. Now, all acid-base reactions produce what? Very good. Salt and water. Anybody remember the definition of a salt? Yeah, it is a halogen. It's this halogen is a salt producer, but this one is going to be a little bit different. Salt. It's the cation of a base. This pen drives me nuts. And the what of the acid? Very good. Cation of a base and the anion of an acid. So that's what a salt is. So you just got to recognize what a acid is. You got to just recognize what a base. And again, you're going to see this tomorrow. Huh? Because I'm teaching it tomorrow. Is that okay? I'm sorry. Too bad.
She's in a bad mood.
That's fine. Last thing. This was kind of weird. Do you need to go back to that?
Yeah.
Sorry.
You're good.
Here. That's it. All right. Let's just go ahead and look at number 4 while it's up there. Why does 4 look different from the other 3? Very good. It's 3 things. This is the only rule you need to know about this. What is CO3? Very good. Please write down. CO3 is carbonate. And this is what you need to know. Carbonates always produce CO2. Carbonate always produces a carbon dioxide. Always produce a carbon dioxide. So I'm never going to ask you to do one of these reactions in terms of writing it. I would just ask you to recognize it. That's all I'd ask you to do. All right. Any questions here? Any questions? All right. We're actually fixing to skip these because I'm going to do that tomorrow because I taught that today. And we're fixing to jump in right here. So skip to the very last one. Redox. Huh? All right. Now, redox stands for something. This is what I want you to write. Redox stands for reduction. What do you think the ox is? Oxidation. Very good. Reduction oxidation reaction. So instead of saying reduction oxidations, we just call it redox for short. Now, I have this cool little acronym. Now, there's 2 of them that you can pick from, and I don't care which one you pick, but you'll just hear me use one of them. Oil rig. Okay? There has to be something for oil rig, but before I go into that, these reactions occur when one compound acquires electrons from another. So that's what I want you to highlight if you have a highlighter. One compound acquires electrons. Now, specifically, I'm talking about electrons. Get chemistry out of your mind for just a second. If I asked you what reduction meant, what does that mean? To go down, right? To become less. I want you to keep that in mind. So if you know reduction means to go down, what do you think oxidation means? To increase. So reduction means to decrease. Oxidation means to what? Increase. Now, this is the hard part. What am I talking about decreasing and increasing? What I'm specifically referring to is their charge. Okay? So think about this. I'm specifically referring to their charge. So if something becomes decreased, do you agree that becomes more negative? Think for a second. If you decrease and your charge, does that become more negative? What are you doing with an electron if you become more negative? You're adding an electron. Why? What is the charge of an electron? Negative. So if I stick an electron on you, what has your charge done? It's become more negative, so it's gone down. So it is kind of tricky, and this is where the oil rig comes in. Oil rig. What it stands for is oxidation is a loss of electrons. Okay? So, oil. Oxidation is a loss. What do you think rig stands for? It's a gain. Very good. So reduction is a gain. So essentially, it's right there. Okay? Reduction is a gain of electrons. It is backwards. That's the tricky part. When you think of reduction, you think of doing what? Losing something, right? But why can't it be technically losing something but be gaining? Because you're losing and gaining negative things. It's tricky. It's backwards. I was going to say reduction is gain. Okay, say it again. Exactly. Exactly. Not energy, but charge. Okay? Now, if you don't like oil rig, there's one more, and it's Leo. What is a Leo? A lion. A Leo says gur. See if you can figure this one out. What? A lion says gur.
Lose electrons oxidation, gain electrons reduction.
Look at Hannah Craig. She just got it right. Very good. So this right here is our Leo says gur. Losing electrons is oxidation. Gaining electrons is reduction. Okay. Well, again, you're going to hear me say oil rig. I like oxidation is a loss. Oxidation is a loss. Reduction is a gain. Okay. But losing and gaining what specifically? Electrons. All right. So let's look at this. Here is what you're really, really going to have to know, and I encourage you to highlight it. Do you see all the things in red? Put big old huge stars and highlight all those phrases. You're going to have to know that. Yeah. All combustion reactions are redox. So here's the great part about this. You've already done this. You remember solving for oxidation numbers? What is it, neutral or charged? Set it equal to. Oxygen is always -2. Fluorine's always. Hydrogen should be a +1. If it's by itself, it's a. All right. So combustion reactions, fuel reacting with oxygens, are always redox. So let's look and see if we can determine what we're looking for is the element in which it's being oxidized or reduced. So is y'all spaced out like this? Yes, it is. All right. So, which one? What do we always want to look for? We always want to look for our zeros first, right? So notice, oxygen is by itself. So what is it? No, it's by itself. All right, so it's 0. Remember, anything by itself was always 0? Yes? Now watch. Please listen. Is oxygen with compounds over here? So what did it become? Both of these became -2. Now, it doesn't matter which one you pick, so watch. Oxygen went from 0 to -2. Did that go up or did that go down? So oxygen was what? Reduced or oxidized? Remember, it was reduced. So oxygen is what? Reduced. Yeah. Laura, first of all, do you agree that oxygen's 0? No, I'm asking. Okay. All right. Now, let's do the other one. Now, this compound, neutral or charged? Set it equal to? Hydrogen is a. So it's +1 here, so that's going to be a what? Okay, so +6. What's the only thing to make that true? But remember, when you go up, divide, so it's going to be a. All right, so notice this. Carbon is a -3, right? Now let's look over here. Let's look at CO2. Set it equal to? Oxygen is? -4. What makes that true? +4, so what's carbon? So notice what just happened. Carbon went from a what to a what? -3 to +4. Did that gain or lose electrons?
Gain.
Stop. If I give something away that's negative, what am I becoming? More positive. Did this become more positive? Oxidation is a loss. Oil. Oxidation is a... So this is oxidation. Exactly. Now, it doesn't necessarily have to go to negative if it just increases. Any increase is oxidation. 2 to 3, it's oxidation. 2 to 1 is a decrease. That's reduction. Let's look at another example. All synthesis reactions are redox. This one's a lot simpler. Do you see any zeros?
Yes.
Where are the zeros?
No, there's no zeros.
Oxidation numbers. Anything by itself is a...
So Na is a zero?
Na is a 0. Stay with me. Na is a 0.
Na is a zero.
Cl is a 0, right?
No.
Yeah, because it's by itself.
That's not.
It's not with another element.
Solo.
Solo. Not solo. Mom, just stop. Seriously, I'm wrong.
Guys, you got to know this either way, so you may want to listen.
Someone call Holmes' mom and tell him that we don't know.
We can just go get her.
No. Yeah, okay, just go get her. She'll laugh at you.
That's what I was thinking. Now, listen. Sodium is a group 1. So what does that tell us its charge is? +1. Well, let's think about it. If I set it equal to 0, +1, so what does chlorine have to be? -1. Well, that one's kind of simple. This one I really should have done first, so I apologize. Sodium went from 0 to what? +1. Chlorine went from 0 to... Which one's easier? I always like to find the one that went down. Which one went down? So chlorine went down, so what is that? It went down. So which means it loses something that's negative, so it becomes more positive. I'm telling you, it's backwards. Listen, look for the thing that went down first. Did that go down? That's reduction, automatically. If it went down, it's reduced. Okay. The other thing will be oxidation. Yes. Yes.
If you think it's oxidation, it's reduction.
So sodium went up.
So it's oxidation.
Bingo.
The more happy it's got, less it's oxidation.
Something about happiness and sadness.
He's gonna write a poem.
All right. All right, please listen. Look. Does it make sense? Sodium started as a 0, then it went to +1. Chlorine started as a 0, went to -1. Did chlorine go down? Stop. It went from 0 to -1. That went down. That's reduction. Bottom line, it went down, it was reduced. So the other thing has to be oxidation. Yes. If it goes up, it's oxidation. I guess if it goes up, think about oxygens in the air, up. All right, let's look at a few more.
What time is it? It's a sticker.
Huh? No. There's only one thing's reduced, one thing's oxidized.
What time is it?
I don't know. No. Let's look at this one. A displacement of hydrogen from water and acid. So let's look at this. Na, please look. Are there any zeros in this one? Na is a 0. Hydrogen. All right, so let's look. Na is a 0. Hydrogen is a 0. What would hydrogen be right here? +1. So let's just look. So notice, hydrogen went from a +1 to a 0. What did that do? It went down. Reduction. Very good. It went down, so it's reduction. Now, Notice this. What was the other zero? Na. Sodium did something. Do we even need to figure out what it did? It oxidized. How do you know that? Process of elimination. We've already found reduction. Sodium had to be what? Oxidized. Yeah. Yep. I mean, that's it. That's all you have to do. That's work. No. No, I'm going to give you that. All you do is look for your zeros and then look and see how it changed. All right, let's look at another one. This one, zinc. Are there any zeros in this? Zinc is. So what is zinc? Zinc is a zero. All right, please listen. Zinc is a zero, hydrogen is a zero. Now, when zinc is with a compound, what is zinc always? Okay, so zinc went from 0 to a 2 plus. Now, did that go down? So it was not reduced, it was oxidized. Is it making sense? Why? Not necessarily. Do what? Yes, H is very good. So this is a plus 1. So what did hydrogen just do? It went from a plus 1 to a 0. What was that? Reduction. Exactly. So it's easier than you originally thought. The key here is look for the zeros. What do you mean? What rules?
It's all different.
They're all different reaction types.
We have to know every single one of them.
Yeah. No. But notice, this is what I want you to notice. Look, I have not taught you combustion yet, but all combustions are redox. So if I ask you, in this combustion reaction, what was oxidized, you can figure it out. Okay? You can move it around. All synthesis reactions, that was the first thing we learned, are also redox reactions. Huh? No. All right, synthesis. Listen, what does synthesis mean? You take A and you take B and you do what? You take A and you take B and you make AB. That's synthesis. Combustion. Remember, I haven't taught you this. You're going to see this tomorrow. It's got to have an oxygen and it always produces carbon dioxide and water. That's combustion. Okay? These last few, remember how we said you went to the dance by yourself? Okay? Notice, NA's by itself, right? Water's the couple. What happened to hydrogen? It got kicked out. Same thing with zinc. Zinc went to the dance by itself, looked for hydrochloric acid, and kicked hydrogen out by itself. That's a single replacement. But even though it's a single replacement, notice what it said. All single replacements are also redox reactions. So it can be more than one type. Okay? Last one. I want you guys to do number 5, those two. See if you can figure out what's oxidized and reduced in those last two, and we'll stop. Yeah, do 5. See if you can figure out what those are. You don't have that? Oh, yes, 4 on y'all's. I'm sorry. Yeah, do both of those.
Teachers, please excuse the interruption. Both the girls and boys varsity soccer games have been canceled. Both teams will be playing those.
Guys, please do these.
5 and 7. Please come out and support our Cougars. Varsity girls will be having practice this afternoon in the gym at 4 o'clock. Thank you.
Guys, please be working on these. Figure out what's oxidized, figure out what's reduced in those last two.
This hurts my head.
What other types of reactions are those? Yeah, but remember, redox is not its own type. It's a part of the other ones. Huh? But it's 4 on yours. It's the same thing. It's mistyped or misnumbered. Those are also single replacements, right?
Yeah.
How can you tell they're single?
Because it being single by itself,
You have one thing.
it takes out CU.
Exactly. So it's just you have one thing in a compound, then it kicks one of those other things out. Both of those are single.
Single replacement.
Yeah. If I have enough time, I am. Bring it to me.
You have 1 minute.
Do I really? Zero. That's a 2 plus, so it's oxidized. But yes. Yes, and yes.
Boom.
But that's a 2 plus, though,
2 plus,
okay? All right. Let me cover this real quick. Is everybody finished? You need a minute. As you're putting stuff up? You don't even have anything else? You don't even have it out working on it?
I just worked on it.
Let me see it.
Let her work it out on the board.
Yeah, come do it up here. That's a great idea. Come do it up here.
I'll do it.
All right. Hang on. So, let's look at the first one. What's your first rule? Look for your zeros. Please listen, guys. Stop. What are your zeros tomorrow?